Alrighty, folks. So now we are going to go backwards a bit uh, to chapter 4, which I don't know if anyone remembers, um, but we skipped it early on in the semester. So in the beginning of the semester, we did chapters 1 through 3, which are, all the vocabulary sections and looking at graphs like histograms and their shapes. And then chapter 3 goes on to do like mean, median, mode, standard deviation, that kind of stuff. And then we skipped straight to chapter 5 with probability, and then from there rolled through normal distribution and kind of kept going. So maybe you forgot, but we did skip chapter 4. I said it fits better at the end of the semester than early on. And it also requires StatCrunch. And around that time of class, a lot of people still admitted that they didn't have it. So we put it off until now. There's no more putting it off. We are going back to chapter 4, which is describing the relationship between two variables. And we start with 4.1, which is scatter diagrams and correlation. We also have to do in this section 4.2, which is regression. So even though this requires StatCrunch, I'm going to be going through 4.1, 4.2 straight through, get all the vocabulary we need, and then I'm going to do examples with correlation or regression, both 4.1 and 4.2 together, so that it minimizes the amount of times I have to switch back and forth between this and StatCrunch. All right, so we start with scatter diagrams and correlation, 4.1. And since the whole chapter is about describing the relationship between two variables, let's identify what the variables are. So, the response variable is the variable whose value can be explained by the value of the, oops, that doesn't look that great, of the explanatory variable. Ugh, undo that. Sorry, my underlining is pretty bad. Still not used to this. So the response variable is the variable whose value can be explained by the value of the explanatory variable. Sometimes you'll hear it called predictor variable. And just to make sure everyone's on the same page, a variable is something whose value is unknown, right? Like someone's shoe size would be a variable because it's different between everyone, and there's a value associated with it. So I hope everyone is okay with the word variable being used, because now we have two different types we're going to be thinking about, since we're thinking about two variables at a time. And the two variables we'll think about is a possible response variable whose value is explained by the explanatory variable or predictor. A lot of times I'm going to say predictor and response. And so kind of going off of my shoe size example, if I was thinking of two variables at the same time, shoe size with, I don't know, age, someone's age would be a good predictor for how big their shoe size is in response, right? Someone who's 2 years old is generally going to have smaller feet than someone who's 30, I would imagine. So there might be a relationship there, I'm guessing, where age helps explain how big someone's shoe size can be. It's worth keeping in mind, though, that of course, maybe I'll make a note of it. Keep in mind that in any scenario, oh, in any scenario, there may be lurking variables that are explanatory as well. And it's been a long time since I've said the phrase lurking variables. I said it very, very early on in the semester when we were talking about collecting samples. But a lurking variable is something that we're not considering, right? So if age is a predictor for shoe size, this is the response. That's not the only thing that, right? It's not just that age determines your shoe size. It's not a one-way street, right? There's other factors that determine your shoe size, I guess, like genetics, which includes your height. I'm going to guess, right? Like taller people generally have bigger shoe size. I mean, that's not the only thing that predicts shoe size either. But there's a lot of things that can factor into how big someone's shoe size is, right? It's not just the age. There could be other things that factor into shoe size. However, I do think there's a relationship. Older people, not children, would have bigger shoe size. Children would have smaller shoe sizes. So knowing how old someone is does give you an idea somewhat of their shoe size, but there are other factors as well that may be lurking. And this is an obvious case of that, where there are other lurking variables out there that would affect how big your shoe size is. But in some other scenarios, it might be harder to think about what these lurking variables are. So we just need to keep in mind that there may be other things at play, other variables at play, other than just our two variables we might be looking at in a problem, like, for instance, age and shoe size, right? There might be other things at play. All right. And now we move on to scatter diagrams. A scatter diagram is, let's underline it, is a graph that shows the relationship between two quantitative variables. Can't graph categorical variables in a scatter diagram. They have to be quantitative. To show the relationship between two quantitative variables, let me erase this. A scatter diagram consists of plotted points. Let's say plotted pairs of variables, values as points on an XY plane. Sounds really fancy. Sounds really fancy and maybe a little daunting, XY plane. But hopefully everyone has seen this before. A scatter diagram is basically a graph of points. And since we're dealing with two variables at a time here, for instance, age and your shoe size, we could plot those in a graph in the XY plane. And if you don't remember how to do that, let me give an example. Plot the point, plot the plot? No, plot the point. Plot the point. 3, 8. If you guys don't remember how to do that, we have an XY plane. Looks like this. You plot the first number first. It gives the coordinates for left or right. So 3. Positive numbers go to the right. Negative numbers would go to the left. So positive 3 would go 1, 2, 3. And then positive 8. The second number you plot using the up and down part. And 8, since it's positive, goes up. If it was negative, we would go down. So 8 going up. 1, 2, 3, 4, 5, 6, 7, 8. Not a great scale, but there's the point 3, 8. And maybe do one more, make sure everyone remembers. Plot the point -4, -7. Maybe not -7, that might be too big. -4, how about +1? Plot the point -4, +1. The first number determines left and right. -4 means go to the left 4. 1, 2, 3, 4. Second number means go up 1. So there's the point -4, +1. So a scatter plot would be a collection of a bunch of points whose values are the pairs for those individuals. So plot the point -4 and +1 doesn't make sense for this scenario, but if I was talking about the age and shoe size, if someone's 3 years old and has a shoe size of 8, that is a crazy, crazy kid. But this would be the point that you would plot. That's insane, right? Actually, I don't have children, so I don't know if 8 is, there's a kid size 8, maybe? I don't know. But this would be the point, age, and shoe size. The predictor variable is the independent variable when plotting in a scatter diagram. You're gonna hear me say scatter diagram, scatter plot. It means the same thing. So the predictor variable is the independent variable when plotting in a scatter diagram, which is the x's. So the predictor for my 2 points were the 3 and the -4, and the response variable is the dependent variable, the y. So you plot the independent or the predictor on the x-axis, and then the y-axis part of the point comes from the response or dependent variable. And again, it's worth noting, remember that there could be lurking variables, right? Not only that, it might be hard to determine which one's the predictor and which one's the response. I think, obviously, this is an easy relationship to know that your age would predict your shoe size a little bit better than your shoe size would predict your age, maybe. But in some scenarios, knowing what's the predictor and what's the response is a little tougher. And we might have to just guess which one's response, which one's dependent, do some research. Anywho, all right, so we keep moving on. So these scatter diagrams that plot points, I mean, with just these 2 points here, you can't really see the picture. Once you get a lot of points together from a sample and plot them, you start to see, hopefully, some shapes. All right, so the scatter diagrams way of seeing if, like actually seeing with your eyes, seeing if two variables are correlated. And we'll get to a proper definition of correlated in a second. But let's just say correlated for now means there seems to be a relationship between them, between the two variables. Oops, between the two variables. So the scatter diagrams are a good way of seeing, like with your eyes, if two variables are correlated. In this class, we will only study variables that have a linear correlation. Or no correlation at all. And what does this word linear mean? Well, it's in the word. If something is linear, if it looks like a line when plotted. So, straight up. Let me give some examples of scatter diagrams or scatter plots. And my question would be, determine if the variables look correlated. If so, is it linear? Oops. All right, so let's go through some examples. Let me just recap real quick. So we have two variables, explanatory and response, or predictor and response. And then we have these scatter diagrams that are going to show the points, and they're the pairs of points, right? So this person whose value was 3 also had a value of 8 with the other variable. This person with this a value of -4 for one variable had a value of 1 for the other variable. That's important, that we plot, this is the same person, this is the same person. It has to be the same person's values being plotted. And why are we doing this? This all says that it's a good way to see if there's a relationship, which mathematically that term means that they're correlated, co-related, means there's a relationship between them. For our class, we're going to be focusing on linear correlations, things that show up as lines. All right, cool. Now we've recapped examples of scatter diagrams, and we want to ask ourselves, do they look related? And I'm just going to come up with some rough pictures because that's what the book does. But let's say here's my scatter diagram. Here's my points, just plotting kind of randomly. There we go. Do these points show that the variables, there's not even any variables to talk about other than x and y. I'm not giving a specific scenario. But in this general example, if I plotted these points, would we say that they're correlated? I would say yes, these are correlated, right? Why? Because there seems to be a relationship between them. The dots go up in this nice line. I mean, they're kind of all over the place individually, right, along that line. It's not a perfect straight line. It's not like the dots connect easily, but there definitely is a pattern. As we look left to right, the dots go up, right? So this is also a linear correlation, I would imagine, because like I said, it follows this line pattern, not a perfect line, right? I wonder, that's not a perfect line, but you see the dots aren't on a perfect line itself, but they do follow that line pattern. So this is a linear correlation. Not only that, this is a positive linear correlation. Which means as one variable increases, the other increases. Right? As we look left to right, this is where, if we look starting from the left to the right, that means we're increasing x, right? Because we're going from negative values to positive. This is increasing in x. As we look from left to right, as we increase x, our y's are also going up, right? So from left to right, that means we're increasing. And as we look left to right, the dots are also increasing. That's what a positive linear correlation looks like, is a straight up and down, not straight up and down, but a line that increases this way. All right, next example. Maybe something like this. Maybe no negative values on this one, only on the positive side. Would you say that these variables are correlated? Do they show a relationship between each other? And yes, I would still say that these are correlated, right? Because they still seem to follow a pattern, still in a line shape too, right? It goes down over here. I mean, we're not using any part of this part of the graph, but that's okay. They're just over here. So I guess x wasn't allowed to be negative. Maybe it was age, I don't know. But it still follows a nice pattern, I would say. And that pattern is linear. They still follow that line shape. I mean, not a perfect line, but nothing in the real world is perfect. So still looks like a linear correlation. The only difference now is that the line that they seem to be following a bit is this is a negative linear correlation. Which means as one variable increases, the other decreases. Oops. So with a positive linear correlation, basically the line goes upwards as you look left to right. With a linear correlation, as we increase our x, our y's start to decrease. So as one increases, the other decreases. So those are the two types of linear correlations, really. A positive one, where as one increases, the other increases, and a negative, where one increases, the other decreases. Let's get a few more examples of scatter diagrams, because they're not going to all look like that, right? All right, here's another scatter diagram for us. Let's say it goes like this. Here are my points. Get a lot of points here so that we can see the big idea. Plotting all these points. Oops, sorry for the zoom in. All right, so there were my first two examples. Here's my next. Are they correlated? I would say no. These points, when plotted, don't look like they're following any kind of pattern. It looks like they kind of were just dumped onto the XY plane, and that's where they landed. I don't see any lines that these follow, right? Like, it doesn't look like that because you still got a bunch of going up here, down here. I don't see any line that this kind of follows, so it's definitely not linearly correlated. Doesn't look like there's any shape at all. The dots are kind of like all over the place, which is going to happen. That means that there's no relationship between them, right? If we see no relationship in a picture, I would say these X's and Y's don't have any relationship between each other. Like my age and, I don't know, how many dogs you own. I don't know. Different people. Like, what does my age have to do with how many dogs somebody owns? And what? I mean, it can't go negative. That's a bad example. But you get the point, right? If there's no relationship between the two variables, they're going to look like this. Just kind of dumped on the XY plane, and that's it. And let's do one more. Last example. Here's the XY plane. Let's say here are the dots for this one. The plotted points. Would we say that these are correlated? I would say yes, they follow a pattern, right? They follow a very strong pattern, almost like waves. They definitely follow a pattern, but is it linear? Does it follow a straight line? No, they follow this wavy pattern, right? So since there does seem to be a relationship, I would say yes, these are correlated. However, this is not linear because it doesn't follow a straight line like these first two examples did, right? And so there definitely are a bunch of different correlations that we could study. I don't know, maybe this is sine or cosine wave. I don't know. That's if you've taken pre-calc. The book has an example of a few others that look like they have a relationship. They follow different shapes. But what we're going to be interested in are these linear correlations. Of course, sometimes we're going to be working problems and we're going to see that there are no relationships between the variables. It looks like this. I just want you guys to keep in mind that there are other relationships that are possible out there, like this one, that does mean that they are correlated. But in our class, since we're only studying linear, we're not going to see cool stuff like this, right? We're only going to see these linear relationships or no relationship at all. These are the three cases we're going to be seeing. But that's only because correlation I can spend an entire semester on. These different shapes have different methodologies on determining mathematically if they're correlated or not. The picture is just a good idea, but it's not the end-all be-all. We still have to do some math. Sorry about that. All right. So let's get to that math. How do we determine... in so I can write. How do we determine if two variables are correlated? Well, first thing we need to learn about is something called the Pearson correlation coefficient. So correlation is measured using something called the Pearson correlation coefficient. And nope, it's not Pearson like the book publisher. Somebody's name, not the book publisher. But correlation is measured using something called a Pearson correlation coefficient. So just like probability was measured on a scale of 0 to 1, it's a number that kind of lets you know what the chances of something happening is, right? Correlation is measured on a scale of -1 to +1. So the Pearson correlation coefficient, the Pearson, I hate that it has such a long name, the Pearson correlation coefficient is measured on a scale from -1 to +1. Inclusive. Inclusive meaning that a Pearson correlation coefficient can be equal to -1 exactly, and it can be equal to +1 exactly, and anything in between. It can't be 7, right? That's outside the range. Can't be -4. It can be 0. It can be 0.64, right? Anything between -1 to 1. There are two ways to denote the Pearson correlation coefficient. And those two ways are R or rho. It's another Greek letter, or a lowercase r. And I bet you can't tell me the difference between them. Same difference as always, right? We use R when we're dealing with the statistic version of Pearson correlation coefficient, and we use the Greek rho when we have the parameter. If we were able to get the data for everybody in the population, match it up, we would use rho. Otherwise, we use R. And of course, we're going to be using R more often in this class because we're dealing with statistics, right? We don't usually have the entire population at our disposal. So, to calculate the Pearson correlation coefficient, which I'm just going to abbreviate as R now, to calculate R is equal to the sum of the what's? The x's minus the mean of the x's divided by the standard deviations of the x's times the y's minus the mean of the y's over the standard deviation of the y's, and all of that is divided by degrees of freedom and minus 1. And this is the the simple linear correlation coefficient. This is actually not even the exact way to calculate R. They made it a simple way to calculate it to get a good estimate, I guess. But if you have the book on page 175 at the bottom, it lists the actual calculation. It's even tougher. And here's why I say you need to get StatCrunch, right? You don't need this. We don't need this crazy formula in our lives. We're going to have to, if we wanted to do it by hand, we would have to use that. But how do we calculate R? We're going to use StatCrunch. And like I said, I'm going to kind of continue lecturing first and not get into the actual how to use StatCrunch just yet. I'll save that for the end after we kind of learn a little bit more. But to calculate R, you can either use this nasty formula that I've already scratched out, or you can use StatCrunch to calculate it for you. I strongly recommend using StatCrunch. But if you want to calculate R on your own, you do that. All right, so R is the Pearson correlation coefficient. It measures if two things are correlated, and it measures it on a scale of -1 to 1. Here's the calculation. We're going to just use StatCrunch for it. Now let's talk about that scale. So if we have StatCrunch calculate R for us, and we get R is 0.86, like what does that mean, right? So let's talk about that scale, -1 to 1. So the scale for the Pearson correlation coefficient, it can be as high as +1, as low as -1, and 0 is right here in the middle, right? So what do these mean? If R equals -1, there is a perfect negative linear correlation. So if you calculate R and it says R is equal to -1, what that means, I'll show you in a picture down here. What that means is you have a perfect negative linear correlation where your dots in your scatter plot are going to look like a perfect negative line, right? That negative relationship meaning it's pointed downwards, but they're going to be perfectly on a line. That would have an R equals -1. I mean, keep in mind, this is handwritten, but let's imagine that's a perfect negative line. That would be an R equals -1 scenario. On the flip side of things, if R is equal to +1, there is a perfect positive linear correlation. What does that mean? Again, I'll show the picture. If there's a perfect positive linear correlation, that means that your dots are situated in a line that is perfectly straight and positive, meaning it increases. What about this case? What if we're dead center? So if -1 is a perfect linear correlation, +1 is a perfect positive correlation. If R equals 0, there is no correlation. Meaning what? That was the case I had up above where they're kind of all over the place, right? There's no rhyme or reason, no lines that it kind of follows. They're just all over the place. Something like this would have an R equals 0. And the scale works that way. If you start at a -1 and go closer and closer to 0, that means your dots are going to get farther and farther apart, look less and less linear. And then as you move to +1, your dots are going to start falling on that positive linear line right here. So last example, let's say I have an R of -0.5. That means that I'm on the negative side, so my dots are following a negative line a bit, but it's not as tight of a line. It's not as perfect as a line as, let's say, R equals -1, right? See, they're still following a relationship where they decrease a bit, but it's not that nice perfect line with R equals -1. It'd be a little bit sloppier, right? The dots have more variation away from that line. And everywhere in between, right? Like if I had R equals like 0.9 up here, it'll look really close to a nice perfect line. A little variation like this, and it would be positive as well. All right, so there's our scale. So we know what the values of R mean. How to calculate it, we know, but really we don't because we haven't used StatCrunch yet, but that's how we're going to get it. We're going to calculate R using StatCrunch. All right. So back to the task at hand is determining if these two variables are correlated. Thanks for hanging in there, guys. This is tough without giving a concrete example yet. Okay. It's worth mentioning that R is not the only thing we need. So let's go to steps to determining if two variables are correlated linearly. So what are the steps? First step, guess how we're going to do this? We're going to actually be running a hypothesis test. So to determine if two variables are correlated linearly, you have to set up HO and HA. Why? Why are we invoking hypothesis testing now? Like, that section was awful. No one really liked it. Why do we have to set up HO and HA? Is because we are running a hypothesis test. HO, HA. The good news is HO and HA will always be the same for hypothesis testing. So always these. HO is that rho equals 0, and HA is rho not equals 0. So you'll get points as long as you have HO is that rho equals 0, HA is rho not equals 0. But what do they mean? Well, if rho equals 0, keeping in mind that rho is the parameter version, right, of R, what does it mean if R equals 0? Well, if rho equals 0, R equals 0, right? Because rho is the parameter. That's if we had all the data out there that we could possibly get. So just know that rho and R are interchangeable in that sense. Just that rho involves every piece of data, whereas R is a statistic. But if rho equals 0, if the Pearson correlation coefficient equals 0, that means there's no correlation, right? That's what this means. If rho equals 0, that means there's no correlation. So that's our first hypothesis, is that there's no correlation. And what does it mean when I say rho not equals 0? When I say rho not equals 0, that means we're getting farther, we're just not equal to 0. We're in one of these other cases. Maybe rho equals -1. Maybe rho equals -0.5. Maybe rho equals +1, right? We're in one of these other scenarios. Anywhere along the line except for 0. If rho is not equal to 0, that means that they are correlated, right? These are our two hypotheses, and you will get points for setting these up exactly like this. Write this exactly. Write that HO, the null hypothesis, is that rho equals 0, which means there's no correlation. Write that HA is that rho not equals 0, which means there is a correlation, because that's really what we're asking, right? So if we're trying to determine if two variables are correlated linearly, there's two options. They either are correlated or they're not. That's why there's only two possible hypotheses for this. What does it mean for two variables to not be correlated? That means their Pearson correlation coefficient is equal to 0. And this checks out because we set up HO with equal signs all the time. What does it mean if two variables are correlated? Well, that means the Pearson correlation coefficient is anything else along this line. It could be -1, it could be -5, it could be +1, it could be anything, right? Those are our two hypotheses. They're either not correlated or they are. And so these have to be the hypotheses you set up. If you set up anything else, I don't know what you would set up. They either are or they're not. All right, so they're set up. Step 2, use StatCrunch. Which means enter the data, run a linear correlation test. So step 2 is use StatCrunch. So you have the hypothesis set up, and then you move to StatCrunch, the application that I hope a lot of people have at least downloaded by now or signed up for. Hopefully you haven't waited all semester and just have done everything by hand. But why do we need to use StatCrunch? Report the R and P value given by StatCrunch. Oops, don't know how to spell StatCrunch. So we need these two things. Maybe I should be highlighting all these important stuff, right? These are the hypotheses we need. And after we use StatCrunch, we need an R value and a P value. So StatCrunch will give you this R instead of having to do this nasty thing up here that I've already crossed out. StatCrunch will give you the R. and something called a p-value, which you've seen this before when we did hypothesis testing. Step 3, if the p-value is less than 0.05, reject HO. If the p-value is greater than or equal to 0.05, the significance level that I've been using for the past few classes, right? Fail to reject. HO. So this is the step where we make our conclusion, either reject or fail to reject. Step 4, if in step number 3, if in step number 3 you rejected HO, describe the correlation using the R from StatCrunch and from step 2. And what do I mean by that? Well, in step 2, you reported your R. Actually, let me make sure to mention, if in step 3 you rejected HO, describe the correlation. That means when you reject, so we're rejecting HO, that means you're rejecting this, right? You're rejecting the idea that there is no correlation, which means you believe there is, right? If you are rejecting no correlation, that means that you think there is a correlation mathematically. So since you do believe, since rejecting HO means you do believe they're correlated, step 4 is to get you to describe the relationship, right? Do we have a negative or positive correlation is the first thing I will look for. So if R is negative, there is a negative linear correlation. That makes sense. If R is positive, there is a positive linear correlation. So it actually works out. The sign of R also determines what type of correlation we have, right? If R is negative, then it's a negative correlation. If R is positive, it's a positive linear correlation, right? Just like here, right? R is negative 0.5, so there's a negative linear correlation. R is positive 1, then there is a positive linear correlation, right? And we can be a little bit more specific, actually. Give me 1 second, I lost my place in the book real quick. Sorry, just trying to find my spot. I'll go off book for a second, I guess. Then use the first decimal place of R to describe the correlation further. If 9, the correlation is strong. If 8, 7, say moderate. If 6, 5, 4, 3, 2, or 1, or 0, I guess, say it's weak. And these numbers, that's just what I would say. If the first decimal place of R is a 9, say it's strong. If it's 8 or 7, I would say it's moderate. If 6, 5, 4, 3, 2, 1 or 0, I would say it's pretty weak. And that's it. Those are the steps. And I know some people may be lost right now, so I like doing this like little recap thing, especially through the videos. We have two variables at the same time, something like age and shoe size. Is there a relationship between them? I don't know. The relationships we'll study are only going to be either linear or just not correlated at all, no relationship whatsoever. We're not going to do these fun, weird shapes. We're only going to be focusing on lines or no lines. Those are the two types of relationship. How do we determine mathematically if there is a relationship? We can't just look at the picture, unfortunately. That would be nice. But the way we do it mathematically is analyzing the Pearson correlation coefficient. If we had every piece of possible data, we would be using this row thing and not even be doing this hypothesis test at the end. But a lot of times we only have R's available, right? We only have statistics. It's impossible to go out there and talk to everyone. So to calculate R, there's this really nasty thing that the book tries to teach us. We're not going to worry about that. We're only going to use StatCrunch. This R that you can calculate either using this nasty formula or StatCrunch is measured on a scale of -1 to 1. In the middle of that scale at 0 means there's no correlation whatsoever. As you move farther away, it becomes more and more perfect. On the positive side, they become positive linear correlations, with 1 being a perfect straight up and down line. And on the negative side, it'd be a perfect negative line, right? Negative slope. And then anywhere in between, the dots can follow a line shape, but not nearly as perfectly. And how do we determine if two things are correlated? Yes or no are they? Well, we set up HO and HA. These are always the same hypotheses. After we do that, we enter the data into StatCrunch and run a linear correlation test. It's in one of the menus, and I'll show you an example in a little bit. And after you do that, StatCrunch will spit out an R and a p-value. The p-value is what determines if they're correlated or not. If the p-value is less than 0.05, we reject. Greater than 0.05, fail to reject. This is exactly like hypothesis testing for proportions, right? We found a p-value. If it was smaller than our significance level, we rejected. If it was greater than our significance level, we couldn't reject. The lucky thing is here that these mean the same thing no matter what, right? Reject HO will mean that you are rejecting no correlation, which means you believe that there is. So reject means yes, there is a relationship. They are correlated. Reject means yes, they are correlated. Failing to reject, meaning you're not rejecting this, you're not rejecting no correlation, means you're keeping it, you're retaining it, whatever you want to say. This is the idea you still have. If you fail to reject, that means there is no correlation. If in step 3 you ended up rejecting, which means you did say they are correlated, well then you should describe it. Tell me what kind of relationship we have. And that's why you need that R value from step 2. Is if R is negative, say the correlation is a negative linear correlation. If R is positive, it's a positive linear correlation. Going further, if that first digit of R after the decimal place is a 9, you can say it's strong. 8 or 7, say moderate. Any other number, you can say it's weak. And that's it for testing correlation. Normally now I would actually do examples so that you guys can see these notes in practice. But what I'm going to do instead is I want to move straight into regression before I have to use StatCrunch. And that's because regression in 4.2 also requires StatCrunch to do. So I'm actually going to change these notes. Well, no, it's already chapter 4. I'm going to move on directly to 4.2. So that's the end of 4.1 right there. If you want to stop, take a break, I don't know, decompress for a second, I totally understand. But I'm going to move straight into 4.2 because there's things in here we also need in StatCrunch that come up when we do this. When we do this step 2 in correlation, the regression stuff from 4.2 also pops up, so it'll be nice to just know what everything is before moving on to StatCrunch. So, moving on to 4.2 is least squares regression. And you'll just hear me call this section regression for short. All right. So luckily this section is kind of short because we only need a few things from it. Give the definition first. The least squares regression line least squares regression line is the line that minimizes the sum of the squared residuals it is determined by y equals b1x plus b0, where a lot of you hopefully recognize this is the equation of a line, right? Y equals mx plus b. But for some reason in statistics, we like switching things up. We call it b1 and b0 instead of just m and b. But where b1 is the slope and given by b1 is equal to r times sy over x, sy over sx. It's that r that we find when we're testing if they're correlated in the first place times the standard deviation of the y's divided by the standard deviation of the x's. And also, let's see, b0 is the y-intercept given by b0 is equal to, it's the mean of the y's minus b1 times the mean of the x's. You actually don't need any of this right here. This is not needed because StatCrunch will provide these when running a correlation test. So just like I'm not going to expect you guys to calculate R on your own. I'm not going to expect you guys to calculate this B1, B0 nonsense because StatCrunch is going to be providing you what this least squares regression line is. And it might be a good idea for me to kind of illustrate what this means. Like this part right here, where is it? Is the line that minimizes the sum of the squared residuals. What the heck does that mean? What that means is, let's say we have our xy plane, we have our scatter plot, and we have our dots, right? I'm going to try to keep it only a few dots. Now these seem to follow a linear relationship because they do kind of follow a line, right? And let's see, let me try to plot that line. I'll make it a dotted line. They kind of follow this one, I'd imagine. I mean, that's not perfect, but that's about it, right? And there's actually a lot of lines I could estimate, right? I could guess that one, or, I mean, I guess they could follow this one in purple. I don't know, which line do you think they follow? Right? There's a lot of lines that these kind of follow pattern-wise, but there's one specific line. I'm going to get back to my red. There's one specific line that minimizes the residuals. What are residuals? I keep saying that. There's one line that minimizes the difference between where the dots actually lay. Like, let's say this dot. This distance away from my predicted line right here This is the residual. Because the actual dot in black, the actual piece of data I found, and my predicted line, my regression line in red, this is the leftover basically, right? This residual is what's left over between my regression line. It's the distance between my regression line and my observed value at that point. And each of these points have a residual associated with them, right? There's almost none there. There's a lot there, a lot here. See, they're all off the line a little bit. And so this regression line in red, this least squares regression line, minimizes the distance between the observed points and that line. And that's the point I'm trying to make, is the computer's going to do this for us. The computer's going to figure out what that red dotted line is, so that we don't have to figure out where, what line minimizes these residuals, minimizes the distance between the actual observed points and this regression line that they're supposed to be following. Of course, the residuals on like a perfect correlation, there would be none, because there's a line that I can draw that's straight through it. But as long as the correlation is not a perfect linear correlation, maybe there's some variation between where the dots lie, well, then there's going to be this least squared regression line. Anyway, I hope I haven't lost anyone yet. Just know this is important for me to teach so you guys know where it comes from, but just know that StatCrunch is going to spit out this red dotted line right here, the equation for this red dotted line. And what is that red dotted line? It's basically the line that the dots are following. I mean, there's some leftovers, they're not perfectly following the line, but this is the line that they seem to be following. That's what a least squares regression line is. It's the equation of the line that the data seems to be following. All right, so why do we need a regression line? The least squares regression line helps us estimate the value of one variable if given the value of the other, if and only if the variables are linearly correlated. Basically what I'm saying is, since we have the equation for the line that these dots are supposedly following, if I ask for, let's say here's x, here's y, if I ask what is the value when x is here of y, you can say, oh, well, it'll be around this point on the line, right? So you can come up with the pair x, y by just using that regression line. But that's only if they're correlated. If they are not correlated, make sure to mention this, if two variables are not correlated, the regression line equation cannot be used. If you say two things are not related, they're not correlated at all mathematically, and then I say, okay, well, predict x when y equals this, you should say, but I can't. There's no relationship between them, between x and y. There's no relationship, so I can't predict one over the other if you give me the value, right? I can only predict the value of one if given the other if I know that there's a relationship. If they follow this nice line, nice least squares regression line, then okay, yeah, I can pinpoint where on that line is as long as you give me the value of one variable. If they're not correlated, you cannot use the regression line. So that's why we need to kind of do these two things together, correlation and regression, because if you go through the test, you find out they're not correlated, then you should not be doing anything with regression. If you go through the test and you say, oh yeah, they are correlated, then you can move on to this regression stuff. But you cannot use the regression equation, not, if you say that there's no relationship. Because if you're saying there's no relationship and then you start using this least squares regression stuff, this assumes that there is a relationship, and you're not allowed to do that if you just said that there's not one, right? I can't stress this enough. So what happens if asked, if asked to predict the variable, the value of one variable given the value of another, if the variables are correlated, substitute the value of the variable you know into the regression equation and solve for the other. So if two things are correlated and I ask you predict this value x if y is 8, and you know that x and y are correlated, then you can just substitute that value I gave you, 8, into the regression equation and solve for the other variable. If they're not correlated though, if the variables are not correlated, find the mean of the variable you're trying to predict. And that's it. You don't. So for instance, like I say, let's say shoe size and height. I think they're probably correlated, right? If I tell you I have a big shoe size, like I wear a size 14, then you're gonna guess, well, you're probably a tall person. That there seems to be a relationship there. I'm gonna guess, and then I say predict how tall someone is that has a shoe size of 8. Well, then you can use whatever regression line you find, because there's probably a relationship between them. Put in 8 for shoe size and figure out what the height is. That's a real thing that you can try to do as a prediction. But if two variables are not correlated, let's say my shoe size and your grade in the class, well, then if I say my shoe size is an 11, now predict your grade in my class, you're going to be like, well, why did you tell me your shoe size? I don't need that. The best prediction for your grade in the class would be, okay, what does the average person get in next class? You don't use the fact that my shoes are in a size 11, right? You just guess, all right, well, what does the average student do in his class? And that's my best prediction on what I'll do, right? Something like that. So if the two variables are not correlated and you're asked to predict the value, just find the mean. Ignore the other variable because you just said that there's no relationship, and just find the mean, and that's your prediction. Otherwise, you can use that other variable in the regression equation to solve for the other, and that would be a better prediction than just the mean, because you said there is a relationship. All right, I think that's everything from the section mathematically. There's just a few last points that I need to make that are super, super, super important. Be careful. Give a couple exclamation points for here. There are two big things I want you to take away from this section before we get into actual examples. Be careful. The first thing to be careful of is, and that you probably have heard this phrase before, is correlation does not imply causation. Correlation does not imply causation. Just because two things are correlated, let me write this down actually. Just because two variables are correlated does not mean one causes the other at all. Just because we can show that there's a mathematical relationship, there seems to be a relationship between these two variables, does not mean that this variable caused the other. There's a few famous examples of this. There's one that shows that butter sales in Maine is correlated with divorce rates in the United States pretty strongly, that there's a strong relationship between how much butter is being sold in the state of Maine with how many people are getting divorced in the United States. That doesn't mean that if Maine starts to sell more butter, that more people are going to get divorced. There seems to be that relationship, but it makes no sense, right? And in that example, it's funny because it's like, of course, how much butter the state of Maine sells does not cause more people to get divorced. There's probably another lurking variable there, right? Underneath, maybe time, population of the United States. Is it growing over time? And so more people are buying butter and more people are getting divorced? I don't know. But there's other variables underneath that might explain why one is seemingly affecting the other. But correlation does not imply causation. Just because two things are correlated does not mean one causes the other. Another example, I think I've said this in class before, is that life expectancy. Your life expectancy generally goes up if you own pets. That does not mean that if your 110-year-old grandmother is on her deathbed that you go buy her a puppy, right? Because it doesn't mean that people with pets will always live longer. Or how about my shoe size example? Just because I wear a size 13 doesn't even mean I need to be tall. I could be average height, right? Or short. Just because two things have a relationship does not mean one causes the other. And I will make sure to test you on that. I'm pretty sure the project has a question like this. In real life, these questions happen. Oh, well, there seems to be a relationship. That means that if I increase someone's shoe size, they're going to get taller. No, that's not how it works. And the other thing I want you to be careful of is do not extrapolate when working on a regression problem. Okay, well, what does that mean? Do not use values far outside the original range of data. Okay, so this one's a little bit, correlation does not imply causation is like a famous phrase. It's pretty easy to understand. Just because two things have a relationship doesn't mean one causes the other. being careful to not extrapolate might be a little harder to kind of understand, but extrapolation means that you're going outside the original range of data, and things might get a little dicier after that. So let's say I sample like everyone in our class, for how much money you guys make and your GPA. I don't know. And I find that there seems to be a relationship. It seems to be that the more money you make, the better in class you do. You got a higher GPA. I don't know. I'm making this up. But then I'm asked to predict the GPA of someone who makes $1 billion every year. Well, that $1 billion every year is probably really, really far outside the range of my original data, which is my students. I'm not going to expect anyone close to making $1 billion is in my class, in my original range of data. And so if I started to use that $1 billion in my regression equation, that's extrapolation. You're now going so far outside the range of data that you were originally given that maybe the regression equation won't work, right? Because that original regression equation that we get from StatCrunch is designed from the data we give it. And if the data we give it was for people with salaries, between 0 and let's say 100,000, and now I'm trying to put in someone who makes $1 billion, that's so far outside their normal range that my regression equation probably isn't equipped to handle that. It'll try to, but I doubt that it's going to be correct, right? It'll try to do it, but don't extrapolate. Don't go if you're given something so outside your normal range of data, just say I can't do this. It's too far away from what my data is kind of set up to handle. Let me quickly look through the section, make sure to see if there's anything else I want to mention. I don't think so. The book goes on to make sure that you guys know what slope is. Would give a line, but hopefully, it's part of the prereqs for CCBC that you know what slope is. But maybe I will point that out too. Let's use this line. On this red line, the slope is rise over run. So rise over run, rise over run. The slope, if you express it as a fraction, can give you the context of the problem. So like if you have the book on page 195, it explains slope in words. But like I said, hopefully you guys already are comfortable with slope since it's part of the prereqs. If not, you can email me, right? All right, let me just see. If there's anything else I want to do in here. I don't think so. I think that's everything we want to do in this section. Yeah, they go through some stuff doing it by hand. Maybe I will mention that in case people are still against getting StatCrunch. I don't know. Maybe I don't put those in the official notes. I really want people to get the StatCrunch. Yep. All right. I don't see anything else that the book wants us to talk about. So that's the end of the lecture for this. Let me do one more recap. Where we're trying to ask ourselves if two things are related. We're going to only be focusing on lines, positive or negative correlation, linear, or not correlated at all. We're not going to do any of this fun stuff. How do we determine if two things are linear? We're not going to do some hardcore math. We're going to set up a hypothesis test with these as our hypotheses. Use StatCrunch to get an R and P value. After we get those, we can determine if they're correlated or not. If your p-value is small, we reject. That means they are. If they are, so if your p-value is small and they are correlated, you can go on to describe it as either a positive or linear correlation. Then you can also say if it's strong, moderate, or weak. And then not only that, you can use this regression line that StatCrunch will also provide for you to help predict the value of one variable if given the other. And the two things I want to make sure that everyone is careful of in this section is correlation does not imply causation. Just because two things are related doesn't mean one causes the other. and do not extrapolate. Do not try to use your regression equation to predict the value of one variable if you're given the value of another, and that value you're given is significantly farther away from the rest of your data originally was. All right, and that is it. I'm going to create another video with actual examples so that I can be doing them in StatCrunch instead of this note-taking app. So that is it for this video. The next video is going to be strictly examples. All right, so make sure you watch that one next.